Hello, this is Patrick Morris from Arizona Thin Film Research, and today I'll be going over the presentation of geometry-dependent thin film uniformity and large area sputtering with rotary cathodes. To begin with, we're going to start off with a rectangular chamber, and on the top surface of that rectangular chamber, we're going to have our substrate motion plane, which the substrate can move either direction along over the top of two rotary cathodes. Now, those rotary cathodes are 650 millimeters long. They have a 100 millimeter TTS from the target outside of the material to the surface of the substrate, and a 200 millimeter target spacing between the central axes of rotation. The magnetic field on these targets is provided by sputtering components. It's using their TRM magnet bars, and we produce the tangential magnetic field on the surface of both the targets shown here. And both of the magnet bars are pointed straight up towards the actual substrate. If we take and we unwrap the target surface and look at the tangential magnetic fields, we can see that the uniformity of the magnetic field is basically perfect along the straightaway, and then it drops down some at the turnarounds. If we take the molecular flow from the intensity of that magnetic field and project that onto the surface of the substrate, we get the corresponding deposition profile, which would be a static deposition profile on a non-moving substrate. And then if we take all of that deposition profile and basically project it to a single edge, say the top edge there, and collect that, we can get what would basically be a dynamic uniformity. So the same as moving the substrate across the uniformity or the deposition zone of the chamber. And with that, we have a higher deposition rate in the center of the target, and then it drops off towards the ends. And so we need to identify the correct area that for our substrate to get the uniformity that we're looking for. So the standard uniformity that most everybody is looking for is plus or minus 2%. And to calculate that out, you typically use the substrate width would be the target length minus 4 times the target to substrate distance, which in this case is 100 millimeters times 4 is 400 minus the 650 gives us that 4 times TTS of 2% uniformity within that 250 millimeter wide substrate zone. What that doesn't take into account, though, is the Lorentz force. So far we used just the magnetic field. And if we go back and we actually look at the electric field as well as the magnetic field, and then look at the force of the electron on the actual electrons from the Lorentz force, and use that, we can get a better estimation of what the uniformity profile would look like. So we're no longer using magnetic field only uniformity simulation, which assumes that the electric field is 0. We're now actually putting in electric field. So we'd begin by putting a minus 900 volt potential on our target and a 125 volt potential on our anode, assuming this is in a cathode pair with the top one being the target and the bottom one being the anode, and running either AC or pulse DC or bipolar pulse DC, whichever way you're interested, but just running it. So one is always the anode and one is always the cathode, and swapping back and forth. The chamber walls are set to a grounded potential. The substrate is set to a dielectric. And if we actually plot the Lorentz force intensity on the surface of the targets, we can see that the target that has the cathode bias on it has a stronger Lorentz force at the turnarounds and a little bit weaker along the straightaway. If we unwrap that and take a look at it closer, we can see that the straightaways are fairly even with each other in intensity, and the turnarounds have a little bit higher intensity. And if we compare that to the magnetic field strength, the magnetic field had that perfect uniformity along the straightaways all the way up until just about the turnarounds, and the Lorentz forces have kind of the opposite. The turnarounds are a little bit stronger, and the center straightaways are a little bit weaker. Now, when we plot the deposition profile of both of these, the magnetic field in blue and the Lorentz forces in green, we can see that they're very similar. When we put the uniformity zone on there, we can see that they're both basically within that plus or minus 2%. The Lorentz forces fall a little off on the left-hand side, but overall, they're pretty similar. And both of these are static fields. So they completely are just using the static electric field and the static magnetic field. And in that 250 millimeter wide substrate, we don't see any real large variation with either of these static simulations. And that's because those static simulations ignore the space charge. And so if we actually take and put electrons into our static magnetic field with our static electric field in there from the cathode to the anode, and then allow them to move around and change the space charge, we'll actually see a completely different uniformity profile. So in this simulation, I've inserted electrons, which are the black dots, and they are moving around the racetrack in the direction of the Lorentz forces and hitting the background gas, which is at about 3 millitorr, and are creating ions, which are the purple. And in the simulation, the electrons are moving all around. They form little clouds and kind of group around, and it's never a completely uniform, continuous plasma. It always has these like little waves that are moving through it. And then the electrons are also moving out and collecting on the walls of the chamber and on the anode on the opposite target surface. Now, if we take that deposition profile, the ions that are collected on the surface of the target, we can see that they are stronger on the turnarounds and weaker on the straightaways. And there's a little bit of an asymmetry. So the right-hand turnaround is a little bit stronger on the top. The left-hand turnaround is a little bit stronger on the inside racetrack. And if we take and compare all three of those, the magnetic field, which had the perfect straightaway intensity, the Lorentz forces static that had the fairly even straightaways with the higher intensity at the turnarounds, and then the accumulated ion impacts of 10 microseconds, which has the much higher intensity at the turnarounds with a little bit of a cross cathode or cross corner effect that is going on from one racetrack to the other as they lead into the turnarounds. So if I take that ion intensity and I run through the same molecular flow simulation and do the deposition onto the surface of the substrate, and then of course integrate that to a single edge for our moving substrate material, we can see the red plot, which is the collected ions, and how that compares to the magnetic field in blue and the Lorentz forces in green. We now have a high point around minus 100 millimeters from the center of the substrate, and a tilt from the left to the right with a decrease in the deposition rate, but a much broader and even much more uniform within our original 250 millimeter wide zone deposition profile. And so you might even be tempted to look at that deposition profile. We can take, if we flip the second cathode around, so the deposition profile of the second cathode is the white line, and our original ion collected deposition profile is the red line, and then we have the summation of both of them together, which is the yellow dotted line. So with that, we produce a fantastic uniformity, like better than plus or minus, close to plus or minus 1% for the deposition profile of these two targets together as the substrate passes by them. And you might even be tempted to go from that 250 millimeter wide substrate to something like a 350 millimeter wide substrate if you need that plus or minus 2% uniformity, because you're still going to be able to hit it within that. But it comes at a cost. There's heavy target erosion at the ends of the target in comparison to the straightaway. So these targets are going to be well below that 85% target utilization. They're going to be closer to like 60%. And, vacuum systems are expensive. Target materials are expensive. Everything around making thin films is expensive. So, smaller is cheaper. Capital equipment, if it can be smaller, it's less material, lower cost. So how can we get there? Can we move the targets closer together? Can we go from that 200 millimeter spacing to 175? Can we optimize the volume on the inside of our deposition system to have a smaller chamber, to use less steel or aluminum or stainless? Can we go closer to the substrate with the targets? Can we make that TTS from 100 millimeters down to 75 millimeters, which gives us that wider uniformity zone? So now we don't have to buy as long of a targets to coat the same area. So if we take all that and we make the walls closer as well, and then we go back and we look at our Lorentz force. Now, remember, this is just static magnetic fields and electric fields. So now what has changed is our magnetic field is the same, but our electric field is now taking the wall into consideration. In this particular one, the wall is grounded. And that grounded wall has increased the intensity of our Lorentz forces on the outside racetrack and decreased it on the inside racetrack, because now I have a very close wall that my electric field is coupling to. Even though we're still running this as like an AC or pulse DC pair, and the walls are not part of the electrical circuit according to the power supply, the electric field potential is still going to be affected by the grounded potential walls. And so if I compare that to the original Lorentz forces, we can see, again, the inside and outside racetracks are basically the same. And then the Lorentz forces with the minimized volume system has the high intensity racetrack on the outside and the low intensity on the inside between the two targets. And if I go and I run my charged particle simulation, again, with this setup, with the grounded walls and the volume optimized, we can see that the electrons are still moving around on the inside racetrack, where we have a little bit lower intensity of the plasma than on the outside racetrack due to that change in the Lorentz forces. But we get a similar uniformity profile of the actual electrons landing in the locations on the chamber. And as we look at the actual ion collection on the surface of the target, we can see something that mirrors the Lorentz forces a little bit. We have a higher ion collection intensity on the outside racetrack and lower on the inside. And we have a high bias, kind of it's stronger on the right-hand side of the top racetrack heading towards the right-hand turnaround. And so if I plot the uniformity profile for this, the baseline model is, again, that red curve, and the current model with the volume optimized is the blue curve. So we have completely mirrored the original uniformity. We've moved the maximum deposition point from that minus 100 millimeters in the red curve to about a plus 100 millimeters on the blue curve by just changing the electric fields that the target is seeing, even though we have the same cathode potentials. So if we look at our 350 millimeter wide substrate, which we would now be expecting with the 75 millimeter TTS, you can see that we're on a single cathode deposition profile. We're well outside of our plus or minus 2% zone that we would be targeting. But if we do that 180 degree rotation, or that mirror for the second target, and then collect both of those together, you can see that we're well within our plus or minus 2% uniformity on our 350 millimeter wide substrate. So while the individual targets are not able to produce the uniformity, together the integrated uniformity of the two targets onto the dynamically moving substrate produces a uniformity that's well within the original specifications. Now, if we go from grounded walls to dielectric walls, so say you started with a silicon target and we're sputtering SiO2 or silicon nitride, the walls, even if they were initially grounded, will eventually become coated with an insulating material. And that dielectric will then change how those static electric fields are formed. So if we look at the Lorentz forces for a dielectric coating on the walls, we've flipped again. We've gone from strong on the outside to now strong on the inside. And you can also see that the anode is starting to approach the same sort of Lorentz force intensity, because now we're truly getting to a point to where the majority of the electric field potential is between the cathode and the anode, and we've really taken the chamber ground out of the actual circuit. And so if we unwrap it and look at the intensity, you can see the large deviation where we're going from north of 350 watts per millimeter squared on my Lorentz force to closer to 150 to 200 range on the outside racetrack. So almost cutting it in half, which is also going to increase the impedance of the target. So it'll make your target voltage go up for the exact same pressure and materials, and will change your process working points. So we can actually see that as we run the charged particle tracing model. So as we insert our electrons into the system, you can see on the outside racetrack, as those electrons come around the turnaround, how far apart they're moving as compared to the inside racetrack where they're really tight and close together. So that's going to spread out that the ion creation on the outside racetrack and keep it very concentrated on the inside racetrack. You can also see that for the 10 microseconds that we just ran here, without changing anything but the chamber geometry, same pressure and everything, our plasma intensity did not become nearly as large as the other models. And that's because the impedance, the actual electrical impedance of this process, having the dielectric walls, makes that impedance much higher and reduces the efficiency of the electrons in the racetrack to ionize the background gas. So then if we plot the deposition profile from the ion collected uniformity profile, we've again moved that deposition profile back to the left-hand side. So in the previous one, it was on the right-hand side, and now it's on the left-hand side. And you can see that there's a much larger hump and a much greater change in the uniformity for the individual target. So the red one is the first target, the white one is the second target, and the again, the dotted yellow line is the summation between the two. And you can still see that within our 350 millimeter wide substrate, we're still able to hit that plus or minus 2% uniformity with the collected sum of both targets. And the individual targets are producing a rather terrible uniformity. We're more like plus or minus 4% on the individual targets, which is going to have multiple impacts. One, the target utilization is going to be very poor. You're going to have a very slanted target utilization that'll slant opposite directions for each target. And then you'll also have, if we are doing a dielectric material like silicon oxide or silicon nitride from a silicon target, there's going to be film gradients. There's going to be a change in the index of refraction through the thickness of the stack of the two targets onto the substrate. So where I have a really high deposition rate, I'm likely going to have a fixed amount of oxygen or nitrogen, and so I'll have a high sputter rate to a lower reactive gas concentration. And then on the red curve on the right hand side of the 0 point, I'll have a low sputter rate to the same reactive gas concentration. So I'll have a higher reacted species on the right-hand side of the red curve and a lower, closer to metal mode on the left-hand side. And so that's going to make a film that is going to be really hard to get like a nice index match on. And there's going to be gradients in the actual film that'll be deposited. But you'll look at the uniformity, the actual thickness uniformity, and say, hey, this is well within our plus or minus 2% range. So in conclusion, the integrated uniformity does not equal the individual cathode uniformity. The uniform thickness does not equal film homogeneity. So, as we just discussed about the change in the reactive process from one target to the other, as we're trying to control it, say, from a central source, from a central gas manifold between the two cathodes, you're not going to be able to compensate for the tilt in the deposition profile from one cathode to the other. Uniformity does not equal target utilization, so we can have fantastic uniformity within spec, but your target utilization could easily be, well below your 80, 85%, closer down to like, 60% target utilization with these deposition asymmetries. And non-uniform issues are not always caused by magnetic field. So often people, first thing they look at when they see a uniformity profile, go, oh, are the magnets okay? And often, as we showed here, I can move that uniformity all around just by changing the local electric fields in the system, which can actually change over time, say as you go from a grounded chamber walls to an insulating chamber walls when depositing a insulating coating. And understanding the plasma uniformity relationship is the first step to process optimization. So if you don't understand how your individual targets are sputtering and what deposition profile is coming off of them, it's really hard to, say, tune your index of refraction or other coating properties that you may be looking to tune. So future simulation work that I'll be looking at is optimization of process zone geometries to minimize the plasma density gradients, plasma development as a function of the power supply and connection impedance. So the cable from the generator that can have a very large impact on the plasma formation due to the impedance of the cable, and target erosion from the plasma density, and uniformity over the target lifetime. So as that target actually wears away, especially if it wears away asymmetrically, how is that going to change the uniformity profile over time compared to, say, targets where we're able to keep the target material wearing away symmetrically? And uniformity as a function of magnetic adjustments. So one of the easiest ways to actually go back and tune the individual system is to go back and make a change to the static magnetic field. And that can help compensate for some of the changes in the electric fields that form as a function of the actual plasma production process. And thank you very much for your attention.